Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
A singular figure emerges from the annals of technological innovation, a mind that consistently probes the boundaries of proprietary systems and redefines the very notion of user access. George Hotz, often characterized by the public as a prodigious hacker, represents a more profound force catalyst for change, a persistent questioner of technological gatekeeping, and an early architect of a more open digital future. His early endeavors centered on a fundamental tension, a dynamic that continues to shape our interaction with the devices that permeate our lives. This tension arose from the increasing tendency of consumer electronics manufacturers to impose stringent controls over their hardware and software, effectively limiting the user's ability to modify, enhance, or even fully understand the products they purchased. The digital landscape of the early 21st century was rapidly evolving, marked by the ascendancy of powerful, interconnected devices that promised unprecedented convenience and capability. Yet, alongside this promise came a growing trend toward what might be termed digital enclosure. Corporations, understandably focused on revenue streams, intellectual property protection, and curated user experiences, began to implement sophisticated mechanisms to lock down their creations. This approach, while offering a degree of perceived safety and uniformity, simultaneously stifled innovation from the user base and created a barrier between the owner and the full potential of their technology. The very devices designed to empower individuals were, in many respects, designed to constrain them within carefully defined parameters. It was within this environment that Hotz's early work gained significant traction. His focus was on dismantling these digital enclosures, on revealing the underlying architecture of these sophisticated machines, and, crucially, on enabling users to reclaim agency over their own property. The act of reverse engineering, often perceived by the uninitiated as mere technical curiosity, served a far more significant purpose in Hotz's hands. It was a method of deconstruction, a process of understanding through dissection, that aimed to expose the mechanisms of control and, by extension, to offer pathways around them. This was not about malicious intent. It was about asserting a principle that ownership of a device should extend to its full functional capacity, unburdened by artificial limitations. Consider the burgeoning era of the smartphone, a device that rapidly transitioned from a communication tool to a personal computing hub. For many, the allure of these sleek, powerful devices was immense. However, the operating systems and the accompanying application marketplaces were meticulously curated. Access to the full spectrum of the device's capabilities, the ability to install software not sanctioned by the manufacturer, or even to fundamentally alter the user interface, was systematically prevented. This created a paradox. A device of immense personal power was, in practice, subject to the dictates of its creator. The user was an operator, but not necessarily a proprietor in the most complete sense of the word. Hotz's early contributions illuminated this disparity. His work demonstrated that the seemingly impenetrable walls erected around these consumer electronics were, in fact, permeable. By meticulously analyzing the hardware and software, he uncovered vulnerabilities and developed methods to bypass the restrictions. This was a testament to a deep understanding of systems, a capacity for logical deduction, and an unwavering persistence in the face of complex challenges. The outcome was liberation of these devices, allowing them to perform functions and run applications that their creators had not intended or explicitly permitted. This act of technological liberation resonated deeply within a growing community of users who chafed under the restrictive policies of major technology firms. The ability to customize, to experiment, and to extend the functionality of one's own device became a powerful symbol of digital autonomy. The Hotz's interventions were not simply about enabling new features, they were about affirming the user's right to interact with their technology on their own terms. He provided the tools and the knowledge that allowed ordinary individuals to engage with their devices at a more fundamental level, fostering a spirit of exploration and empowerment. The implications of this early work extended beyond the immediate gratification of unlocking a device. It served as a potent demonstration that technological control, while often presented as a necessity for security or user experience, was also a mechanism for market segmentation and revenue generation. Hotz's actions implicitly challenged the narrative that users should passively accept the limitations imposed by manufacturers. He highlighted the potential for innovation that could arise when users were granted greater freedom to tinker, to adapt, and to build upon existing technologies. This created a ripple effect, inspiring a generation of technologists and users to question the status quo and to explore the possibilities that lay beyond the officially sanctioned pathways. The ongoing debate surrounding digital rights management, the ethical considerations of software ownership, and the very definition of the user's control over their purchased devices owe a significant debt to these foundational interventions. Hotz's early explorations were not isolated incidents. They were early manifestations of a persistent philosophical stance regarding the relationship between individuals and the technologies they employ. They laid the groundwork for a broader conversation about digital freedom and the inherent right of users to modify and personalize the tools they own, a conversation that continues to evolve and shape the technological landscape we inhabit today. His work established a precedent, a clear signal that the boundaries of proprietary control were not immutable, and that a deeper, more liberated engagement with technology was not only possible, but actively being pursued. The digital realm, particularly the burgeoning world of personal computing and its extension into mobile devices, presented a fascinating landscape of innovation alongside carefully constructed limitations. For many users, the advent of the smartphone, a device that promised unprecedented connectivity and computational power, also brought with it a tightly controlled ecosystem. This environment, designed for seamless user experience and robust security, also inherently restricted the autonomy of the individual owner. The ability to customize, to extend functionality beyond the manufacturer's intended scope, or to explore the underlying architecture of the device was deliberately curtailed. This curated experience, while beneficial in many respects, also fostered a quiet undercurrent of desire for greater openness, for the freedom to tinker and to truly own the digital tools in one's possession. George Hotz emerged as a pivotal figure in this unfolding narrative, his early interventions directly confronting these carefully managed digital frontiers. His work on the iPhone, specifically the development of the first widely recognized jailbreak for Apple's revolutionary smartphone, represented a profound statement on user agency and the nature of technological ownership. The problem Hotz addressed was the closed architecture of Apple's iOS operating system. This system, while celebrated for its intuitive interface and the curated experience offered by the App Store, maintained a strict gatekeeping function. It prevented users from installing third-party software not approved by Apple, from modifying core system functions, and from accessing the device's file system without explicit permission. This created a powerful, yet ultimately restrictive, digital environment. Hotz's solution was to meticulously deconstruct the security mechanisms that enforced these limitations. His achievement, often referred to as the spirit jailbreak, was a testament to his deep understanding of software vulnerabilities and his persistent drive to uncover them. This was a process of identifying and exploiting a specific weakness within the iPhone's operating system that allowed for the execution of unauthorized code. The significance of this act extended far beyond the simple ability to install custom applications. It demonstrated, unequivocally, that the seemingly impenetrable walls of the iOS ecosystem were permeable. It revealed that the user, if equipped with the necessary knowledge and tools, could indeed reclaim a degree of control over their device. The development of the jailbreak sparked a crucial debate within the nascent smartphone community concerning the nature of tethered versus untethered access. A tethered jailbreak required the device to be connected to a computer and run through specific software each time it was rebooted. This was a significant inconvenience, highlighting the ongoing challenges in maintaining persistent access beyond the manufacturer's control. An untethered jailbreak, conversely, allowed the device to retain its modified state even after a full power cycle, representing a more complete liberation from the original constraints. Hotz's early work contributed to the understanding and eventual achievement of both states, pushing the boundaries of what was thought possible within the iPhone's architecture. The impact of this early intervention resonated powerfully throughout the technological landscape. It fundamentally altered the perception of smartphone security. What was once viewed by many as an unassailable fortress of digital protection was revealed to have exploitable weaknesses. This revelation spurred a wave of subsequent security research, both from those seeking to replicate and expand upon Hotz's findings and from Apple itself, working to patch the discovered vulnerabilities. The ongoing cycle of exploit development and security patching became a defining characteristic of the smartphone era, a dynamic tension that continues to shape the industry. Furthermore, the demand for the flexibility and customization that jailbreaking enabled served as a powerful, albeit indirect, catalyst for the evolution of the App Store model. While Apple's App Store provided a controlled and curated environment, the desire demonstrated by users to install a wider range of applications and to modify their devices' behavior underscored a significant market for expanded functionality. This pressure, coupled with the technical demonstrations of what was possible, contributed to the broader conversation about user choice and the potential for a more open mobile ecosystem. Hotz's actions, therefore, played a role in shaping the very trajectory of mobile computing, highlighting the inherent tension between proprietary control and user freedom, a tension that continues to be a central theme in the digital age. His early work with the iPhone was a clear signal that the established order of technological control was open to challenge, and that the pursuit of digital liberation was a potent driving force set the pursuit of digital freedom. A thread woven through George Hotz's early endeavors found a new and formidable canvas with the advent of the PlayStation 3. Sony's console, a marvel of engineering and a bastion of proprietary control, represented a significant challenge to the burgeoning hacker community. Its security architecture was designed with an explicit intent to create a closed ecosystem, safeguarding intellectual property and dictating the terms of engagement for its users. At the heart of this defense lay a sophisticated security layer, a hypervisor intended to act as an unbreachable gatekeeper, preventing any unauthorized code from running on the powerful hardware. This system was a testament to the era's burgeoning understanding of hardware-level security, a complex arrangement of checks and balances designed to ensure that only some sanctioned software could execute. The problem, for those seeking to explore the console's capabilities beyond its intended function, was the sheer ingenuity of this design. It was a carefully constructed fortress, seemingly impervious to the usual avenues of software exploitation. Yes, ever drawn to the intricate puzzles presented by closed systems, turned his attention to this formidable challenge. The PlayStation 3, with its robust cell broadband engine and its layered security, presented a problem of a different magnitude than the relatively more accessible iPhone. This was not merely about bypassing software restrictions. It involved a deep dive into the console's boot process and its fundamental operating principles. The hypervisor, a privileged piece of software that managed the underlying hardware and the operating system, was the ultimate target. Its function was to enforce strict security policies, ensuring that the system remained in a trusted state for UFS and others. Understanding how to subvert this hypervisor was the key to unlocking the console's full potential. The task required not just clever coding, but a profound understanding of low-level system architecture, reverse engineering, and a meticulous approach to uncovering subtle flaws in complex designs. The breakthrough arrived from a meticulous dissection of the console's inner workings, specifically focusing on the mechanisms of secure code execution. UFS identified a critical vulnerability, a flaw in the way the system handled digital signatures. This exploit, often referred to as the gatekeeper vulnerability, provided a pathway to circumvent the hypervisor's protective measures. The essence of the discovery lay in the ability to craft and sign custom code that the PlayStation 3 would, under specific conditions, accept as legitimate. This was a profound revelation, as it demonstrated that even highly sophisticated hardware-based security systems could possess exploitable weaknesses. The problem Sony sought to solve by isolating the system was, in essence, undone by a clever manipulation of the very trust mechanisms it relied upon. The discovery was not a brute force attack, but an elegant exploitation of a design oversight, a testament to UFS's analytical prowess. The public disclosure of this vulnerability marked a pivotal moment. It effectively allowed for the signing of custom firmware, granting users unprecedented control over their PlayStation 3 consoles. This opened the door to a realm of possibilities previously unimaginable within Sony's carefully curated environment. The implications extended far beyond simply playing imported games or running homebrew applications. It represented a fundamental shift in the balance of power between the manufacturer and the user. The ability to run unsigned code meant that developers could experiment with the hardware, create entirely new applications, and explore the console's capabilities without the constraints imposed by Sony. This was a powerful demonstration of how a single vulnerability could dismantle a carefully constructed security apparatus, highlighting the inherent limitations of proprietary control in the face of determined exploration. The modern relevance of UFS's PlayStation 3 hack resonates deeply within the ongoing discourse surrounding hardware security and user freedom. His achievement underscored the fundamental truth of that no system is entirely invulnerable, especially when its complexity increases. The hat-and-mouse game between console manufacturers and the security research community, a dynamic that continues to shape the landscape of digital entertainment, was significantly influenced by this event. Sony's efforts to secure its hardware were met with an ingenuity that exposed the limitations of their approach. This ongoing struggle highlights the continuous evolution of security measures and the equally persistent innovation in methods to bypass them. The PlayStation 3 hack served as a potent reminder that the pursuit of open access and the desire to push technological boundaries are powerful forces that continually challenge established paradigms of control. The impact of this exploit extended to the broader understanding of hardware security architectures. It demonstrated that even robust systems, when subjected to rigorous scrutiny and creative analysis, could yield to unexpected vulnerabilities. The hypervisor, intended as an unbreachable barrier, became a focal point for demonstrating how low-level system design could be manipulated. This contributed to the ongoing refinement of security practices within the electronics industry, prompting a deeper examination of how trust is established and maintained within complex hardware and software interactions. The lessons learned from UFS's work informed subsequent generations of console design and security protocols, even as the fundamental challenge of securing complex digital systems persisted. It was a clear signal that the era of absolute hardware control was gradually giving way to a more dynamic and contested digital frontier. The accessibility of the PlayStation 3 hack, once the core vulnerability was revealed, also contributed to a wider democratization of console modification. While the initial discovery required significant technical expertise, the subsequent dissemination of information and tools allowed a broader community of enthusiasts to engage with the altered console environment. This fostered a culture of experimentation and innovation, leading to the development of new applications and functionalities that Sony had never envisioned. The console, once a closed platform for gaming, transformed into a versatile computing device, capable of tasks far beyond its original design parameters. This transformation, catalyzed by UFS's foundational exploit, illustrated the latent potential residing within powerful hardware when freed from restrictive software limitations. The desire to explore and expand the capabilities of consumer electronics proved to be a potent engine for innovation, often outpacing the intentions of the manufacturers themselves. The PlayStation 3 hack thus stands as a significant historical marker, illustrating the enduring tension between proprietary control and the persistent human drive for exploration and customization within the digital realm. The PlayStation 3 hack thus stands as a significant historical marker, illustrating the enduring tension between proprietary control and the persistent human drive for exploration and customization within the digital realm. This impulse to unlock potential, to repurpose and enhance would soon find a new and far more ambitious canvas. The nascent era of autonomous driving presented a landscape dominated by immense capital investment and proprietary research. Developing self-driving capabilities was, for all intents and purposes, the exclusive domain of major automotive manufacturers and well-funded technology giants. The sheer complexity of the undertaking, involving sophisticated sensor arrays, powerful onboard computing, and vast data sets for machine learning, placed it beyond the reach of individual engineers or smaller, independent teams. The problems of their time were manifold: the prohibitive cost of specialized hardware, the intricate software architectures required for real-time perception and decision-making, and the legal and ethical frameworks that were only beginning to be considered. This created a significant barrier to entry, effectively confining the advancement of autonomous technology to a select few, fostering an environment where innovation was inherently centralized and controlled. The promise of a future where vehicles could navigate our roads independently remained largely a distant vision, accessible only through the products of these large entities. George Hotz, ever drawn to the edges of what was considered possible and accessible, recognized this concentration of power and the resulting limitations on widespread innovation. He saw an opportunity to democratize the very concept of autonomous driving, to transform it from an exclusive corporate endeavor into a collaborative, community-driven pursuit. This ambition coalesced into the Comma.ai project, a bold initiative to build an autonomous vehicle platform that was both achievable and adaptable for enthusiasts and independent developers. The solution Hotz proposed was elegantly pragmatic: leverage readily available hardware, much of it repurposed from consumer electronics, and combine it with open-source software principles. This approach directly countered the prevailing model, which relied on bespoke, expensive components and closed-source development cycles. The Comma.ai project sought to demonstrate that the core challenges of autonomous driving could be tackled with accessible technology. Instead of proprietary LiDAR units costing tens of thousands of dollars, the team explored the use of more affordable sensors, including cameras and radar systems that were becoming increasingly common in consumer vehicles. The computational backbone often involved powerful, yet relatively inexpensive, single-board computers or even modified gaming consoles, echoing the spirit of his earlier exploits. The software stack was built upon open-source frameworks, allowing for transparency, modification, and community contribution. This ethos was central to the Comma.ai vision. It was not merely about building a single self-driving car, but about creating a blueprint, a set of tools, and a methodology that others could adopt, adapt, and improve upon. The goal was to foster a vibrant ecosystem of developers, all contributing to the collective advancement of autonomous technology. The modern relevance of this approach is profound. At a time when autonomous vehicle development continues to be dominated by a handful of major corporations, Hotz's Comma.ai project served as a powerful testament to the efficacy of open innovation. It challenged the notion that such complex technologies must remain within the confines of proprietary research labs. By demonstrating the feasibility of building functional autonomous systems with accessible components and open-source software, Comma.ai highlighted the potential for a more distributed and participatory model of technological progress. This resonates deeply in a world increasingly reliant on intelligent systems, suggesting that the future of advanced technologies might be better served by collaborative efforts rather than exclusive control. The Comma.ai project, therefore, represents a crucial early articulation of a philosophy that seeks to broaden access to cutting-edge technology, empowering a wider community to contribute to its evolution and shaping its ultimate direction. It underscored the idea that significant technological leaps could emerge from the collective ingenuity of many, rather than the singular efforts of a few. The trajectory of George Hotz's endeavors, particularly following the foundational explorations with Comma.ai, pivoted towards a tangible manifestation of open innovation within the automotive sphere. This phase addressed a clear inadequacy in the prevailing landscape of advanced driver assistance systems, or ADAS, for consumers. The sophisticated functionalities that promised enhanced safety and convenience were frequently ensconced within prohibitively expensive manufacturer packages, often with limited customization or interoperability. The underlying challenge was the proprietary nature of these systems, which effectively created technological enclaves, restricting user agency and stifling broader development. Hotz's response to this environment was the creation of OpenPilot. This initiative represents a direct application of the principles demonstrated by Comma.ai, translating the concept of accessible, adaptable technology into a functional driver assistance system. OpenPilot is an open-source software stack designed to provide and enhance ADAS capabilities. Its core innovation lies in its philosophy, leveraging existing hardware, specifically the Comma.ai device, and fostering a vibrant community of developers and users to continuously improve its performance and expand its feature set. This approach directly confronted the limitations of proprietary systems by offering a transparent, adaptable, and community-driven alternative. The problem Hotz identified was that while automotive manufacturers were introducing ADAS features like adaptive cruise control and lane keeping assist, these were often basic implementations, and access to them was tightly controlled. The software was a black box, inaccessible for modification or enhancement by the end user. Furthermore, the cost barrier meant that these advancements were not universally available. OpenPilot sought to democratize this technology. It aimed to provide a platform where a user could install a system that offered comparable and often superior performance to factory-installed aiders, while simultaneously benefiting from ongoing development driven by a global community. The unique solution offered by OpenPilot was its open-source architecture. Unlike the closed, proprietary systems of established automakers, OpenPilot's code is publicly available. This transparency allows for deep understanding, modification, and extension of its capabilities. Developers can contribute bug fixes, performance optimizations, and entirely new features, creating a rapid iteration cycle that outpaces traditional automotive development. The system integrates with a range of vehicles that are equipped with compatible hardware, effectively retrofitting advanced driver assistance capabilities onto a wider array of cars. This adaptability and extensibility are central to its disruptive potential. Consider the core functionalities often found in premium ADAS packages, maintaining a set speed and distance from the vehicle ahead and keeping the car centered within its lane. OpenPilot replicates and often enhances these features. The system's ability to learn and adapt is a direct result of the collective input from its user base. When users encounter specific driving scenarios or edge cases, they can provide data and feedback that helps refine the algorithms. This distributed intelligence model allows OpenPilot to tackle a wider variety of real-world driving conditions than a system developed in isolation. The community aspect is paramount. It transforms the user from a passive recipient of technology into an active participant in its evolution. The modern relevance of OpenPilot is profound. It demonstrates a powerful alternative model for automotive software development, one that prioritizes openness, collaboration, and user empowerment. In an era where vehicles are increasingly becoming sophisticated computing platforms on wheels, the ability to access, understand, and modify the software that governs their behavior is crucial. OpenPilot challenges the traditional automotive industry's approach, which often views software as a tightly controlled, proprietary asset. By making advanced ADAS accessible and adaptable, TTOCS's project opens the door for innovation from a broader spectrum of individuals and organizations. It fosters a more dynamic ecosystem where improvements can be shared and implemented rapidly, benefiting all users. This initiative speaks to a broader shift in how complex technologies are developed and deployed. The success of OpenPilot underscores the power of open source principles in areas traditionally dominated by closed, proprietary systems. It illustrates that significant advancements in safety-critical automotive technology can be achieved through collaborative efforts, driven by a shared passion for innovation and a desire to make cutting-edge features more widely available. The project serves as a compelling case study in how individuals can disrupt established industries by embracing transparency and community engagement, offering a glimpse into a future where the control of automotive software is more distributed and responsive to the needs of its users. It highlights the potential for collective intelligence to refine and advance technologies that were once the exclusive domain of large corporations. The prevailing paradigm in advanced technological development often involves a structured, proprietary approach where intellectual property is meticulously guarded and innovation pathways are typically confined within corporate research and development laboratories. This model, while capable of producing significant advancements, can also inadvertently create barriers to entry, limit widespread adoption, and slow the iterative refinement that collaborative communities foster. A fundamental question arises concerning the optimal environment for fostering rapid, impactful technological progress, particularly in domains that touch upon public safety and widespread utility. The challenge lies in reconciling the desire for controlled development with the immense potential unlocked by open access and collective problem solving. George Hotz's trajectory across diverse technological frontiers consistently embodies a philosophy that directly confronts the exclusivity inherent in many advanced fields. His work, from the early days of mobile device modification to his more recent endeavors in autonomous driving, champions a vision where knowledge and capability are shared and where the process of innovation is inherently transparent. This approach posits that by dismantling artificial barriers to understanding and modification, complex technologies can be rapidly improved, made more accessible, and ultimately safer and more beneficial for a broader populace. The underlying principle is that collective intelligence, when applied to sophisticated systems, offers a powerful counterpoint to the limitations of isolated development cycles. Consider the realm of consumer electronics, particularly the mobile computing devices that have become ubiquitous. The initial restriction of operating system functionalities and hardware access, a hallmark of proprietary design, presented a closed ecosystem. Hotz's early explorations into circumventing these restrictions, often referred to as jailbreaking, were not merely acts of digital curiosity. They represented a profound statement about user agency and the potential for distributed innovation. By unlocking these devices, he demonstrated that a vast community of developers and enthusiasts could identify new uses, enhance performance, and uncover vulnerabilities that might otherwise remain hidden within a closed system. This opened the door for a cascade of applications and customizations that enriched the user experience far beyond the manufacturer's original specifications, highlighting the latent potential within these powerful tools when freed from restrictive controls. vehicles. The ability of individuals to delve into the core of these devices and share their findings fostered a dynamic ecosystem of improvement and creativity. This ethos of openness and collaborative refinement finds its most potent expression in the OpenPilot project. Developing advanced driver assistance systems ADAS is an undertaking of immense complexity and safety criticality, traditionally reserved for well-funded automotive manufacturers with extensive resources and specialized teams. The sheer volume of data required for training, the intricate algorithms needed for perception and control, and the rigorous testing protocols all point towards an endeavor that seems inherently suited to large-scale, closed corporate structures. The prevailing wisdom suggested that such systems could only be reliably developed and deployed within these established frameworks. Yet, AWS and his collaborators have systematically challenged this assumption. OpenPilot represents a paradigm shift, offering an open-source alternative for enhancing vehicle autonomy. The project's foundation rests on reverse engineering existing hardware and software, a process that necessitates a deep understanding of how complex systems function, all while adhering to the principle of making this knowledge publicly available. This transparency allows for a level of scrutiny and contribution that is difficult to replicate within proprietary environments. The problems addressed by OpenPilot are immense: the safe interpretation of complex driving environments, the precise control of vehicle dynamics, and the adaptation to a vast array of driving conditions. The unique solution offered by the OpenPilot approach lies in its distributed nature and its commitment to open development. Instead of a single entity dictating the pace and direction of progress, OpenPilot thrives on contributions from a global community of engineers, researchers, and enthusiasts. This collective effort allows for the rapid iteration and refinement of algorithms, the identification and correction of errors through widespread testing, and the adaptation of the system to a broader spectrum of vehicles and driving scenarios than any single company might realistically achieve. The problems of their time included the high cost and limited availability of advanced driver assistance features, often accessible only to owners of premium vehicles. OpenPilot directly addresses this by creating a pathway for more affordable and accessible enhancements. The modern relevance of this open source strategy in automotive technology is profound. It demonstrates that significant advancements in safety critical systems can be achieved through collaborative efforts, driven by a shared passion for innovation and a desire to make cutting-edge features more widely available. The project serves as a compelling case study in how individuals can disrupt established industries by embracing transparency and community engagement, offering a glimpse into a future where the control of automotive software is more distributed and responsive to the needs of its users. It highlights the potential for collective intelligence to refine and advance technologies that were once the exclusive domain of large corporations. This initiative speaks to a broader shift in how complex technologies are developed and deployed, where the ability to share improvements and implement them rapidly, benefiting all users, becomes a significant advantage. The success of OpenPilot underscores the power of open source principles in areas traditionally dominated by closed, proprietary systems. George Hotz's career, viewed in its entirety, reveals a consistent thread, a profound commitment to technological liberation. He has consistently acted as a catalyst, urging the democratization of complex systems and empowering individuals with greater control over their digital and physical environments. His journey, from unlocking the potential of consumer electronics to pushing the boundaries of automotive software, demonstrates a fundamental redefinition of how we interact with and understand the technologies that shape our lives. This enduring impact lies in his relentless pursuit of open innovation, a philosophy that champions transparency and accessibility, proving that significant technological leaps can emerge from outside the hallowed halls of traditional corporate or academic institutions. He inspires future generations of creators and problem solvers to challenge established norms, to question proprietary encumbrances, and to champion solutions that are inherently open and universally accessible. His work with the PlayStation 3, a feat that involved reverse engineering the console's sophisticated security architecture, represented an early, potent declaration of intent. The problem of the day was the enclosure of powerful computing hardware within tightly controlled, proprietary ecosystems. Sony's PlayStation 3 was a marvel of engineering, a potent platform for gaming and multimedia. However, its potential was largely confined to the applications and experiences its manufacturer deemed suitable. TS's achievement was to demonstrate that the underlying hardware could be liberated, allowing for a broader spectrum of creative expression and utility. His solution involved meticulous analysis and a deep understanding of the system's inner workings, culminating in the ability to run alternative operating systems. This act was more than a technical exploit. It was a philosophical statement about ownership and control in the digital age. It ignited a global conversation about the rights of consumers to modify and repurpose the devices they purchase, fostering a community of tinkerers and developers eager to explore the uncharted territories of the console's capabilities. The subsequent foray into the automotive industry, particularly with the development of OpenPilot, further solidified this ethos. The challenge here was the increasing complexity and the proprietary nature of modern vehicle software, especially concerning advanced driver assistance systems. These systems, while offering enhanced safety and convenience, were often locked down preventing customization or independent modification. The problems faced by drivers were manifold: limited access to software updates, exorbitant costs for feature unlocks, and a general lack of transparency regarding the vehicle's operational logic. AWS's approach, spearheaded by Comma.ai, centered on creating an open-source alternative. OpenPilot emerged as a sophisticated driver assistance system that could be installed on a range of compatible vehicles, offering capabilities that rivaled and, in some cases, surpassed those offered by manufacturers. The unique solution provided by OpenPilot was its reliance on community-driven development and an open platform. Instead of proprietary algorithms developed behind closed doors, OpenPilot leveraged the collective intelligence of a global community of engineers and enthusiasts. This collaborative model allowed for rapid iteration, continuous improvement, and the rapid adaptation of the system to new vehicles and scenarios. The development process itself became a testament to the power of shared knowledge. Contributions poured in from individuals worldwide, refining perception models, improving control algorithms, and expanding vehicle compatibility. This approach directly addressed the limitations of traditional automotive software development, which often progresses at a glacial pace and is dictated by corporate roadmaps rather than user needs or emergent possibilities. The modern relevance of this contribution is profound. OpenPilot has not only provided a more affordable and accessible alternative for advanced driver assistance, but has also served as a powerful demonstration of how open-source principles can be applied to safety-critical systems. It has pushed the automotive industry to consider greater transparency and user empowerment, subtly influencing the conversation around software ownership and modification. The project has shown that significant advancements in safety-critical systems can be achieved through collaborative efforts, driven by a shared passion for innovation and a desire to make cutting-edge features more widely available. The project serves as a compelling case study in how individuals can disrupt established industries by embracing transparency and community engagement, offering a glimpse into a future where the control of automotive software is more distributed and responsive to the needs of its users. It highlights the potential for collective intelligence to refine and advance technologies that were once the exclusive domain of large corporations. This initiative speaks to a broader shift in how complex technologies are developed and deployed, where the ability to share improvements and implement them rapidly, benefiting all users, becomes a significant advantage. The success of OpenPilot underscores the power of open-source principles in areas traditionally dominated by closed, proprietary systems. DHS's career is a testament to the disruptive power of individual ingenuity coupled with a commitment to open principles. He has consistently challenged the status quo, not through confrontation alone, but by building better, more accessible alternatives. His work transcends mere technical skill. It embodies a philosophy of technological freedom. He demonstrated that the barriers erected by proprietary systems, while formidable, are not insurmountable. By dissecting, understanding, and then openly sharing his findings and creations, he has empowered countless individuals and fostered a culture of innovation that benefits everyone. His legacy is not etched in proprietary patents or closed-door research labs, but in the open-source code that continues to evolve, the unlocked devices that offer new possibilities, and the inspiration he provides to anyone who believes technology should serve humanity, not the other way around. He has shown that the future of technology is brightest when it is shared, understood, and accessible to all.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.